on Thursday. I've got them printed out. We have 2 review sessions. So I'm going to do a review now, but you can also attend again with your TAs tonight and tomorrow. And I'll write down the times here, but they're also on Piazza. So the review sessions will be with your TAs tonight from 7 to 8:30 and tomorrow night from 5 o'clock to 6:30. So they're going to be encouraging you to work the test review problems together and answering questions that you have. Yes? Yes, both of those times we'll use the Test 1 review that you can download on Moodle to go over problems. Other questions? So you don't have to have RSVP'd. This room is on the opposite side of the building, on the 3rd floor, and then it's on the right about halfway down the hall, next to the water fountain. Okay, so your test on Thursday is exactly the same format. There are 8 questions. So it's going to look just like this. Well, not exactly, but almost exactly like that. And you'll have all the same type problems. So the first one is truth table. So you'll be given a statement, and you need to prove it using a truth table. So how many variables do I have as inputs? 3. So I need to make those 3 on the left. We actually have a table written for you on the current exam, so you can just fill it out, I think. How many rows do I need? 8 rows. Excellent. Make sure you write these in the right order, because remember that happy graders make happy grades, and they're going to be looking for your table to be in this order. And that's part of what you're supposed to learn when doing truth tables. So please don't do them in another order. Okay, then we look for P implies Q. That is true when what? P is false, or Q is true. So P is false, I can do the first 4 rows really easy. And then when Q is true, it's going to be the last 2, so then I put zeros in the other ones. So S implies not Q. We'll do very similar. So when S is false, that's true. Q is false in that case, so that's true. S is false, so that's true. S is not false, and Q is not false. Okay, that's true. That's true. That's true. And that's false. So basically the only 2 falses are where both S and Q were true there. And then here we're looking for P being false or S being false. Either one of them will make it true. So again, those first 4 being P being false would have made that there. And then we have 1, 0, 1, 0, because that's the opposite of S. All right, then we need to AND these 2 columns together. Very easy. Whenever I get any zeros, remember that ANDs remember zeros. Okay, and then I'm going to check. Star implies square. That's what we're checking. So the left-hand phrase implies whether it implies P implies not S. Okay, and that should be true, because if you actually look at this, that's P implies Q, and that is what? Q implies not S. So with hypothetical syllogism, I actually know that P implies not S. So I shouldn't even have to check it, but I can to make sure I've got my table right. 0 does imply a 1, 0 does imply a 1. I'm not lined up real well anymore, but these are my last three. 0 implies 0, 1 implies 1, and 0 implies 0. That's why we draw a table, because it's hard to stay lined up. Any questions on this? Should be a straightforward problem. If you need extra columns for, not P or not Q or whatever, do that so you don't make any mistakes, because this should be free points. Right? This is 8 points on your exam. Truth tables are the easiest thing we've done so far. No questions? Good. All right, proofs are the hardest, so we're going to do that. So here's your practice proof problem. By the way, I've seen a lot of posts on Piazza about the NovaNet Lab 3. We realized that a lot of you weren't able to log in. You may turn those proofs in on paper. You can also scan them and make a private post on Piazza to your instructor group. You can slide them under my door. Basically, as long as you do the Section 2 proofs, you're going to be fine. I highly recommend that you do them, because that is going to be so much good practice for problems 2 and 3 on the exam, and each one of them is worth 15 points. All right, so you can be lazy and do this. Okay, if I prove by contradiction, what am I doing? I'm negating the conclusion first. There were a couple of questions on Piazza about whether or not you were allowed to skip steps on the test or in NovaNet. NovaNet will let you skip double negation and commutative and sometimes associative, and you can skip all those on the exam as well. So I don't care if you have an extra step for double negation or even say that you did it.
On the NovaNet, it would say your proof is correct, but is that going to count as okay?
Yeah, it counts as okay. So NovaNet allows you to go ahead. If you skip one of those, it just lets you know that you skipped one, just in case you were, thinking that everything was totally perfect. Okay, so that's line 4, not the quantity B and not C. So to do by contradiction, first we actually, remember that I call that negation of the conclusion the money, and we're going to spend it at the store. It's our little store right there. It's a beautiful store. So what we need to do in order to use it is actually to do De Morgan's on it. So we're going to get not B or not C. I'm okay if you skip and do straight to this. So that was line 4 and De Morgan's. And you can also abbreviate your rules. That is fine as well. This is double negation. And I like to go ahead and do implication rule if I have an or, and do simplification if I have an and. So this is an or, so we can turn that into an implication. And these things all came from the negation of the conclusion. I've used 4, 5, and 6. Doesn't mean I can't use them again, but I'm just marking them off to keep track of what I've done so far. Then I go to the store, I take my money to the store, and see what I can get. So with B implies C, I could combine it with line 1, or I could combine it with line 2. Who would like to combine it with line 1? Who would like to combine it with line 2? It looks even, so I'm going to do 1 because it comes first. So we get A implies C from 1 and 7 and hypothetical syllogism. That name comes from hypothetical, has to do with if-then, and syllogism means something that's true. Okay, so we've used this, and now this is money. And we've also used line 1. So we're just checking them off just to note. Now we can do with line 2, same rule. Are we almost done? Yes, we are. Thank goodness. The test problems, proofs, we try not to make them too horrible. So your proof by contradiction is that easy. So if you just keep doing it, you will get done. Okay, so we and those two things together from lines 3 and 9, and conjunction is the rule. And then we write the word contradiction. Any questions on this proof? Yes. Any valid proof is okay. It does ask for a proof by contradiction. If you do it by direct proof, we'll take off probably 4 points. If you do it the cheap way, we won't take off any points. Oh, yes. Any proof that is correct will be marked correct. If, by the way, if you do a proof and you're pretty sure it's correct and it gets marked wrong, just bring it to the TAs during office hours and have it checked. So that's the same for any problem. If you don't like how it was graded, bring it to office hours and have it be checked. Or you can also make a private post to the instructors and say what your question is and like take a picture of your exam and post it, and we'll answer it together. So that's another great way to do that, especially if you want me to look at it. No, you don't have to do the dollar signs. That's just to help you guys focus on what I'm looking at and what I'm doing, and also for you guys. But if you don't need it, don't do it. Okay, no other questions? Any contradiction is fine. So I could, if I had gotten A on one line and not A on another one, and do conjunction with those two, that's fine. And you look like you have a question. Oh, that's okay too. Yeah, if you do that on the test. So the question was, so everybody can hear, if you just tell the line numbers and say that they're a contradiction, I'll be okay with that. By the way, the test is not short. So when you're working it, if you get stuck on something, just turn the page. Go to the next page. Because you need to try to do as much as you can. And we'll give you partial credit for everything that you get down. All right, problem 3 is your direct proof. Again, we'll just number these lines. Now we need to prove A implies C. So the method I do is I look for a proof line that has a similar structure and the same variables. So line 1 looks very promising. So I've got A implies on there. I'd like to get rid of that B. The rule that gets rid of, there are a couple of rules that get rid of things in implications. But one of them is modus tollens, right? So if I wanted to get rid of B, the quickest way to do it is if I had not B. But I don't have that. But I do have not B or not D, and that looks like an implication, because the other way I can get rid of a variable in an implication is hypothetical syllogism. So I'm going to need to change line 3 into an implication. So that was 3 in the implication rule. All right, so now I did line 4 because of wanting to get that B together with line 1. So that's what I'm going to do now, is I'm going to combine 1 and 4 in hypothetical syllogism, and I'll get A implies not D. Okay, so now I've got my A implies, but that pesky not D is on there. It looks like I'm going to have to use it with line 2, so it's going to have to be hypothetical syllogism, but not D doesn't match with the hypothesis of the implication, right? So what do? Contrapositive. So we're going to get not D implies C from line 2 and contrapositive. So we did that on purpose to use with line 5. So we're going to do 5 and 6 and hypothetical syllogism and get A implies C, and that's what I wanted to prove. So we're done. Any questions? Yes. So you just want to explain line 6? Okay, so line 6 came from line 2, which is not C implies D. And remember that that's actually logically equivalent to not C or D, right? And that is also logically equivalent to C or D, which is the same as D or C, right? Which is the same as not D or C, which is the same as not D implies C. And the contrapositive rule actually lets us go straight to that. So the way contrapositive works is I reverse the implication and I negate both sides. It's a little bit like multiplying both sides of a less than or equal to by a negative number, right? Then I have to flop it to the other operator. So in this case, we have to reverse the direction of the implication and negate both sides. Other questions? All right, we'll go to the next one. So problem number 4 is a circuit design problem. And I believe I mentioned in class that I wouldn't give you a problem with 4 variables, and the TA's made your exam, and they might have put 4, but it's not too horrible. So I have checked it myself and worked it. So you won't have more than, I believe, seven terms to do total in here. Let's see, that's not focusing. Okay, so you'll have to read the paragraph at the beginning. It says, when the sum of the inputs is more than 1, then C equals 1. And we want S to be the exclusive OR of the inputs, C0, X0, and X1. What circuit is this? It's an adder, and we did it in class, right? And there's also a truth table for it in packet 2, like page 2. So there's multiple places to look for this, and your book has a really nice chapter on designing circuits, so be sure to check that out if you want more resources. Okay, so it says when the sum of the inputs is more than 1, so I just add these. That's not more than 1. That's not more than 1. That's not more than 1. That one is because it's 2. That's not. That one is. That one is. And that one is. And then S is the exclusive OR of all the inputs. And exclusive OR translates into having an odd number of the inputs being 1. So you can do an exclusive OR of like a bazillion things, and if it's an odd number of bazillion things, then it will be 1. If there's an odd number of 1s, and it will be 0 if there's an even number of 1s, including 0. So 0 is an even number. All right, so exclusive OR of these 3 is 0, and then 1, 1, and 0. 1, 0, 0, 1. So notice that the first half looks like the exclusive OR of 2 variables, right? And the second half looks like the negation of that. So that's because basically the first half is exclusive OR of the last 2, right? And then the last part is the opposite of that. That's why it works. Okay, now we need to write a logical expression for C in terms of the inputs. We will not give you an adder problem, so don't just memorize what the equation is going to be. It's not going to be the same truth table. So you'll have a different truth table. The surefire way to be able to answer it is to use disjunctive normal form, which is to look for all the 1s in the column and write the min terms for those. Okay, so for C, I'm going to write the min terms on the left. So we need a min term at each of these 3 rows. So what we're trying to do is write the state of the universe at each of those rows. So we have C0 is false, X0 and X1 are true. And in this row we have C0 is true, we have X0 is false, and X1 is true. We have C0 and X0 true, and then X1 is false. And then all 3 are true. So if we just OR all these together, C equals all that. And yes, it is fine if you do that. So if you draw an arrow up, I'm fine with that. Not on this page. This page asks you to write the equations, and the next page asks you to draw the circuits. Okay? So part C is to write the S equation, so we're going to write that. Okay, so we need min terms for these 4. I'm just going to write these out for all of them. Okay, and then I'm going to put the knots where they go. Okay, there's some knots for this one. And for this one, So that is disjunctive normal form to find the equation for a circuit when I have the truth table. If you write something because you looked at it and you're like, oh, I know what that is, you can do that. But you're pretty much guaranteed to get the answer right as long as you can do this. So notice that every section tells you how many points it is too. So if you are, getting lost on something, check how many points it is. If you can give up that many, go to the next part. Any questions on this one? So to answer the question, if I just see that it's, not C times x0 exclusive or x1 plus C times x0 exclusive or x1, that is fine. You can write that. Anything that's logically equivalent will be fine. Yes?
So just for clarification, when you're doing the disjunctive normal form, you're seeing for C, for instance.
Yes.
Whenever C is equal to 1,
Mm-hmm.
you're going to look at the states of each individual component, and you're going to say if it's 0, it's going to be not.
Yes.
Whatever that component is 1.
Let me repeat your question for everybody. So when we're doing disjunctive normal form, what we do is we look for ones in the output column that we're trying to write the equation for. And then whenever there's a 1, we see what the values for the variables, the input variables are. And if it's true, I just write that variable down. If it's false, I write that variable with a not over it. And then I AND those together. So all the inputs, I'm going to AND them all together, but I'm going to write down what the value is in that row. Remember that we did this for all of the possible output functions for 2 variables, right? So we generated them by actually making minterms. And what a minterm does is it tells me what's the state of the universe here. So the state of the universe at row 4 is C0 is false, X0 is true, and X1 is true. Remember that that's an AND, so that AND is actually telling me those actual values. It's like me telling you that I have a husband, and I have a son, and I have a car. And I don't have a dog. Right. Yes. So then I OR just the ones for ones together. So don't write all the minterms for all 8 rows and OR them together, because what output function will you get? You'll get the all ones output function. You don't want that. You want the one that you actually wrote the table for. Any other questions? So one thing I want to let you know that we've done is all of your TAs have worked all the problems that are on your actual test, and we timed it. And we're giving you 3 times as long as they took. So hopefully that's enough. Yes? Okay, I heard explain the S column, but I didn't hear the second part of your question. I didn't hear the last part of your question. Oh, well, because the sum bit is the exclusive OR, so I can do exclusive OR with the first 2, and C0 is 0 in this first column, so this is actually the exclusive OR of X0 and X1 in the first 4 rows. Do you see that? In the last 4 rows, it still actually has the same table. If you look, these 2 tables are the same in the first 4 rows and the second 4 rows for X0 and X1. So if I did the exclusive OR for X0 and X1, I get the same output as the top. And then I exclusive OR that with C, which is all ones. So 1 exclusive OR 0 will give me 1. 1 exclusive OR 1 will give me 0. 1 exclusive OR 1 will give me 0. And 1 exclusive OR 0 will give me 1. Does that explain it? We are literally adding up the bits, and so that's the sum bit. So if it's 1 or 3, it's a 1 carry 1. If it's a 3, you carry 1, and if it's not. So that's not even in the carry. So the sum bit's all we're trying to figure out. Okay, all odd numbers have a 1 in the last position in their binary representation. Right? They do. Okay, so now we have to draw some circuits. So we have a function for C. By the way, you are, if you want, allowed to do reduction before you do this part, but I don't recommend it. Because what your TAs are going to do is check to see if the circuit you draw matches the equation that you have. Okay? So if you somehow mess up your equation, as long as you draw your circuit to match that, it's going to be okay. But if you do some reduction in between and that's wrong, how are we going to give you partial credit for that? Especially if you do it in your brain. So if you do it on your paper, that's okay. What I'd recommend that you do is actually just directly draw the equation for what we have. So here's what we have for C. And by the way, this is printed so you can actually see question 4 and 5 at the same time. So your test is double-sided. All right, so I'm going to draw 4 AND gates, 4 big ones with 3 inputs each. Yes. I'm going to do this, and then I'm going to reveal their secret lives, which you are allowed to do. Okay, that's already an OR gate. How about these? They can be OR gates on the inside, but let's go ahead and figure out our knots first. Or actually, we can go ahead and switch them. Okay, let's go ahead and switch them. But secretly, right, if they were ANDs, they would just be, so an AND actually is an OR gate with all the inputs negated and all the outputs negated, right? So we're going to swap those into ORs. We'll just make that a nice fat line. Okay, and all these have to have knots on them, right? By the way, I'm drawing this messy on purpose to show you I don't care if it's a mess on your paper as long as we can read it. I could do nicer. But it's a test. I'm in a hurry, right? Also, I have to have enough time to answer your questions. Yes? Absolutely. All right, so we got our OR gates. Now we just have to figure out what to put on the back. So I have these I've got 4 gates, but since I've just switched them into ORs, they were ANDs originally, right? But since I switched them into ORs, I've got to negate all my inputs, right? So whatever's on here, I have to do the opposite. So I'm going to do my first gate right here. So this is going to be for the term, for the first term. I'm just going to write the terms on here so I don't have to hold this paper anymore. Okay, so wherever there's knots I've got written up here, I've got to put the opposite. So I don't want to put a knot there. I'm just going to put C0 straight in there. Sorry about that. I didn't make a plan for that. Okay, and then I have to put a knot for X0. And I have to put a knot for X1. Right? Because I'm drawing an OR gate instead of an AND gate, yes. You are allowed to do that, but it may be hard for us to read your paper if you do it. So I recommend that you do put bubbles wherever you have a knot. Because we're going to be looking for that, and otherwise we'll have to look twice. And remember, if I have to look twice, it's less likely that you'll get the right grade on the first round. Okay, so for the next one, I'm going to have to do the opposite, so I need 2 knots. And for the last one, for the next one, I need 2 knots. And for the next one, I need 3. If I was confusing you, basically what you need to do is draw the AND gates, and then you can draw the OR gates inside with all the inputs and outputs negated. And then if 2 bubbles are together, just cancel them. So bubbles are the circles for knots. That's what we call them. Okay, so the next question asks us to draw a circuit with only AND and NAND gates for S. So it's nice because our minterms use AND gates, right? And so the only thing we have to do for that one is to change that big OR into an AND. Not this equation, but we're going to have one that looks very similar, right? Except it'll be all AND gates. So I'm going to go to the next one unless someone has a question on this one. Okay, the next problem we're going to do S with AND gates. It's going to be easy because we have 4 minterms. And an OR of everything is the same as an AND gate with all the inputs negated. Now, the cool thing is that if I have done this problem using disjunctive normal form, I know what this answer looks like before I even know what to put on the left-hand sides of the gates. Right? Like, it looks like this. All I have to do now is figure out what inputs to put on each of the gates. Because this number of ANDs, how do I know how many of those are? That's how many minterms I have. And I'm going to OR them all together, which is the same as an AND with all the inputs and outputs negated. So you can use robot brain for this part. All right, now the next part, we don't even have to flip the variables, so we can do not C0, not X0, X1. And the next one has a not on the first and third. And the next one has nots on those two, and the last one doesn't have any. I don't mind if you draw it neatly with the inputs in one place. That is fine. If you don't have enough room on your paper, you can bring some extra paper. We'll also try to have some up here. There's no extra test space on your test. So, okay, this last question, you won't have a question like that, but let's answer it anyway. Okay, it says, if there are 2 to the 16th different logical output functions, how many inputs are there? So we did problem 1 on homework 1 was we actually had to define all the 16 different logical output functions when we had 2 input variables. So there were 16 different functions for that, which is equal to 2 to the what? So 16 is equal to 2 to the 4th, and we had 2 inputs. So what do you think that 4 represents? That's right. It was true or false for each row in our truth table. So we had 2 inputs that made 4 rows in the truth table, and then all the output functions, we could put a true or a false in each output row. So that's why it was 2 to the 4th. So if I have 2 to the 16th possible functions, that means I have how many rows in my truth table? 16 rows. And how many inputs give me 16 rows in the truth table? 4. So this was for the hint. The hint was that I had 2 to the 4th, and there were 4 rows in the truth table. So in this case, that means there's 16 rows, which means that there are 4 inputs. We'll do some more counting later, so like I said, you're not going to have a problem like this, but we'll count some more things later. Okay, if there are questions on that, post them on Piazza. This next question is simply applying De Morgan's to a statement that we give you. I don't recommend trying to understand the statement because we didn't make them to make sense. We only made them so that you can actually use De Morgan's and the implication rule to make it so there aren't any knots or implications left. I do highly recommend that you print out this test and work it yourself, even though you've seen me do it. If you have not worked these problems yourself, you don't know how long it'll take you, and you might be thinking, oh, I understand all of those, but you're going to want to time it out and make sure you can do it in the right amount of time. Okay, we always do De Morgan's from the outside in. Why do we do that? I heard the answer over here partly. Less confusing. That's one good reason, but there's another good reason. It's less work. That's right. I might be able to cancel out some knots, so then I could do less work. And we always want to do less work, right? Because we're computer scientists. We don't like to do stuff more than once. Also, the more stuff we do, the more chance we have for human error, right? So we're computer scientists realizing that humans are always having some inputs having to do, including yourself. So you want to minimize the amount of errors. So I'm going to actually show you what I do with these, and I highly recommend you do the same thing. And you're totally allowed to do it. So what I'm going to do is I'm going to first just move this knot through the quantifiers. Remember that it flips them as it moves through. Knots never disappear, by the way. That bracket's going to line up with that bracket. There we go. So I've done one step, and I'm not going to copy all that stuff down because I will probably make an error. So the next thing I'm going to do is then figure out what the main operator inside those brackets is, because I need to do De Morgan's, and I can only do it with ands or ors. What's the main operator? It's an implication, so I've got to do implication rule first, right? So there's a nice ditto right there. So now I'm going to have an implication. I've got some brackets and an implication and then some parentheses. So the implication changes into an or, and I negate the first variable. If you do exactly the same formatting, we're going to mark this as correct. All right, now I can do De Morgan's, and I still don't need to know what are inside those brackets, right? By the way, before I go any further, does everybody see what I'm doing? Okay, good. So I'm basically just not copying things over. I'm referring to them with what kind of containers they have and where they are. Okay, so now we're going to distribute this knot. So this bracket still gets there. We have not. This first bracket, the or changes into an and, but then we have to do a not in front of those parentheses. Oh, good. These knots cancel out. Even less work to do. Yay. Okay, so I can do this one right now. So let's do that. So what's the opposite of x greater than or equal to w? It's just x is less than w. So remember that less than, the opposite. So if less greater than or equal to is false, then less than is true. So we've just done this part right here. So we're done with that second part, so that's done. This and is going to be a final answer. We're going to need some more room to do this bracket because I didn't put enough room. So I'm going to start over here and draw a little arrow. So that's that bracket. And we're going to put another bracket here and draw a little line, and a bracket there and draw a line, so I can actually do the stuff. Looks like I'm done because I don't have any implications or knots, right? So now instead of a ditto, I'm going to copy these out. So I do have a final line that has everything on it. And we're done. I'm sorry, that was smashed. By the way, we left more spaces for you, so you can copy them down directly in columns. And your TAs actually made your test in LaTeX and found like different size brackets. It was very cool. We had fun today. If it sounds like fun to you, maybe you want to apply to be my TA next year. No thanks? Yeah, I know most of you don't want to. It's all good. Any questions about this one? If you don't want to do it this way, it's fine. As long as you get the final answer, you're fine. And if you write down what you're doing, and immediately, if you make a mistake, we will try to check that. Any questions? Okay, we'll do the last two problems, and then after I go through them, we're going to go back to the proofs, and I'll have you work them at your seat and check them with your neighbor to see that everybody can do them. I'm going to apologize right now because the actual problem for this on the exam is a lot harder than this. So, remember I told you in class the other day that there would be a tricky one? There is a tricky one, so there's a bunch of knots in the one on the test. Okay, so remember that under the quantifiers we have to have logic values, and under our letters we're going to have frequency values. And what I mean by frequency values are our weird, all true, all false, at least one true, at least one false values. Okay, what do I fill out first? The there exists x p of x and the there exists x q of x. So under the there exists, I'm going to write the truth values for the full statement. And then I can go ahead and add those together. And then for p of x and q of x, I want to put their frequency values. And you are allowed to make more columns if you want. I just don't have a lot of room on this paper, and this fat marker doesn't let me have more room. Okay, so if there exists x p of x is false, that's what we have in row 1. What can we say about the frequency of p of x? It's all false. So everywhere we have a there exists and something to figure out for it, we're going to put all false. And then everywhere we have a 1 for a there exists and we're trying to figure out frequencies, we're going to put at least one true, right? So a lot of times when I teach you how to do something in this class, I'm giving you the most clever and quickest way to do the problems without having to think through them a lot. So you're kind of getting a tool set to use later, so you know what truth tables are. If you get a problem later, you know how to make a truth table. You know how to fill it out. Now you know how to do one for predicate calculus and figure out when things are true and when they're not. Okay, so now we can't fill this out until like second to last, but we can do the p of x and q of x frequency table because we're going to AND all false with all false. And remember that ANDs preserve falses, right? So if I see any falses, I'm going to keep them. So these first 3 rows all have all falses somewhere, so those are easy. The last one, we're going to AND at least one true with at least one true. Do we know anything about the truth value for that? No, we don't, because AND only knows about falses. Because if I have at least one true, like let's say I have a blonde person in the room and I have at least one blue-eyed person in the room, that doesn't actually tell me whether there's a blonde with blue eyes or not. So it could be true, it could be false. We don't actually know, so we put a question mark. And then we figure out the truth values for the quantifier, there exists. So for all false, we know we have zeros for there exists. And then for a question mark, we have 0, 1. By the way, I won't count off if you just put a question mark in there too. So both of those will be fine. Because we can't tell. That's what question mark or 0, 1 means. Both of them mean, I don't know. It could be this or that. All right, now we're going to check whether the implication goes from column 1 to column 2. So 2 is the output of my left-hand side and 1 is the output of my right-hand side. I'm going to see, does 1 imply 2? Well, in the first 3 rows, 1 is false, so the implication is true. And in the last row, 2 is true, so the implication is going to be true because it doesn't matter if 1 is true or not. So we get a 1 there. By the way, you will have a problem that's asking you for this, for going both directions. And so maybe one of them might not be all 1s. So don't just fill out all 1s if you see one of these, because you're going to have to check and see which one is correct. By the way, if you like to make extra columns for your stuff and you need lots of room, you could turn your paper this way and make your table however you want, or draw whatever columns you want. As long as we can grade it, and tell what you did, you're fine. So with a lot of knots on this problem, you're going to need some more columns. Okay, last problem. It's not actually marked like this. It just says like 15 points or something on here. So the way the exam works is that we have 110 points on the exam, and each problem has its points on there, and we count your final grade out of 100, which is basically means that you're dropping a 10-point problem, or you do them all and we grade them, and whichever you did best on is what you're getting your grade out of. And it's possible to get 110, so that's extra credit, which means that if you bomb another test, you're getting points towards it on this one. So, by the way, the average for test 1 in my class in general is usually above 80. So this is the easiest test. I have gotten some feedback that it would be nice if the hardest test was first, but we can't do it. So the next test is going to be the hardest one. So you can get ready now. This is the easy one. It's partly easy because you're nervous, like you're not sure how we're doing a test, and you're probably going to study more for this one. But I'm telling you, however much you study for this, record that and do more next time because you need it. Okay. This says, suppose that the universe for P is all people and the universe for D is all people. So we have a function called f, and it is that person P can fool person D. Write the following statements in English. So we have, there exists P for all D, f of PD. So that's like there's a person, right? And this for all D is everyone. So you can do some intermediate stuff, but basically there's a person that can fool everyone, right? Or who? So this is not an English class, so I'm not going to be too terrible about grading this. However, if it's too mangly and nobody could understand it in English, I want you to try to write it better. So what does that mean? If I were to say something like, no one doesn't have any cars, you would be like, what? So if someone would do that to you in regular conversation, please try to rewrite your sentence. Now, that was a double negative, right? What can we do with double negatives? We should be able to cancel them if we move them around with De Morgan's. It is totally legal for you to take a problem and move the knots however you want before you write the English. That is totally legal, because all we want is a statement that is logically equivalent. It doesn't have to exactly match the predicate calculus statement that we have given you. Okay? So you are allowed, if there's knots in there and there's 2 of them, you should move them around until they cancel each other. And then you can write a totally positive statement, which is a lot easier. Okay, so on the next problem, you could write predicate calculus for what's given, or you could move the knot to the outside, write the predicate calculus for the positive statement, and then reverse it, because we are very good at saying what the opposite of an English statement is, right? Like, I have some cookies. Very easy to make it opposite. I don't have any cookies, right? So it's much easier to do if we move the knot to the outside. So I recommend that you do that. So I'm going to do that for this problem. If I move it to the outside, then I have for all D, there exists P, f of PD, right? That is logically equivalent. So now I'm going to write the statement for, or I'm going to talk about the statement for all D, there exists P, F of PD. So that means everyone can fool someone, right? The opposite of that is not everyone can fool someone. Oh, you're right. The D is first. So the D is the person getting fooled. Sorry, I made a mistake. So this is everyone is getting fooled, right? So for each person, I can find someone who can fool them, right? So I actually think this one would be easier if I move the not over 1. I think this one might be the easiest one to write. So you can move the nots wherever. Makes it easier to write. So this says, there's a person that no one can fool. Right? So not there exists is no one. So that is for my there exists D, not there exists P solution. Let me write one. It's logically equivalent. So I can move the not with De Morgan's, but any De Morgan's makes logically equivalent stuff. So the English will be logically equivalent, and that is fine. That is all you need. So I don't want you to write a mangled up English sentence just to match the logic exactly. So let's try to write the sentence for the original statement just for practice, okay? So this statement says, there's someone being fooled. So there's someone that for each person, they cannot fool them. Right? I mean, so we don't usually speak with language like that, right? So it says there's someone so that for each person, that person cannot fool the first person. That's awkward. You can write it, right? So that's what I would write. If I was going to write this in English, I would just exactly the way it's written. So that's how I'd write that if I was going to write directly what that says. There is someone so that every other person cannot fool them. And that's technically not exactly right because other means not that person. So the statement as it's written actually means that person can't fool themselves either. Right? But I'm not going to mark off for that. That's right. Someone cannot be fooled by anyone. That is correct also. That is a better way to write this one. So sometimes you have to write a mangly sentence and then try to figure out a better way to say it. So that's also correct for part B. So these are all B. Okay, I'm going to copy C down because my pen just doesn't fit in this space. Okay, so this says for all D, there exists P, F of PD. So this person is getting fooled, right? That's doing the fooling. So for each person, I can find someone who can fool them. So how do you say that? Everyone can be fooled by someone. A question you should ask yourself when you write your English is, how many people is each of these describing? So when I say everyone can be fooled by someone, how many people are doing the fooling? How many foolers are there? Potentially how many? Could be a lot, right? If that there exists was first, there should only be one. So this looks good because there could be a lot in my English sentence and there could be a lot in my predicate calculus sentence. So I want to make sure that they match up. Any questions about this one? So it's also fine to say, there is, for each person I can find someone who can fool them. That is fine also. So I recommend I can find after a for all. Yes? No. You don't have to write any other logic. Yes. That's right. It's not the same as someone can fool everyone because that would actually be this statement. Right? That is someone can fool everyone. Remember that English actually tries, if we speak regular English, we actually try to put the independent variables first, and independent variables come first in predicate calculus. So the independent variable for this is each person getting fooled is an independent variable, and the person doing the fooling depends on the person being fooled. In this case, I define the person doing the fooling before I find the other people who are getting fooled. So that's an independent variable because I figure that out before I figure out the rest of the people. So the English actually tells you the same order that you should have in your predicate calculus as long as you have a regular English sentence. Okay, let's see what part D is. Okay, what does that say? Everyone is clearly the first thing. And then they're doing the fooling, so I should go ahead and write can fool. And then someone. There we go. If I reverse the order of that, it reverses the order of the sentence. So that is, someone can fool everyone. We already did that one. No, I'm sorry. Someone can be fooled by everyone. Everyone can fool someone. Someone can be fooled by everyone. Sorry about that. So someone can be fooled by everyone. So the D is the person being fooled, so I had to say can be fooled since that person came first. All right, let's do part E. So this one we actually are given a statement and we have to figure out the predicate calculus. So this one is, there's someone who cannot fool anyone. Okay, I want you to try this one. So I'm going to show you my process. I want you to take what you have on your paper. What I do is I figure out the predicate first. So I usually write f of PD first, and then I figure out if it needs a negative in front of it. So it says cannot fool, so it should have a negative right in front of the fool, because the English has put in the negative right in front of fooling, right? And this someone is clearly there exists a P because they're doing the fooling. And anyone is what? That's a for all because it really means everyone that has a not somewhere near it. So there is a person so that for all the people, they can't fool them. So you can figure out your predicate, whether it has a not. You can figure out your quantifiers and then figure out the order, which is almost always going to be the same as the English order. Yes? Is it acceptable to have the not in front of the everyone? If I say not everyone, that's not the same as everyone not, right? So yes, I can have a not in a different position, but then anyone I would have had to have a positive F statement, right? And then a not, there exists D. So that's the other way to do it. So if I write F of PD as my first attempt at the predicate, then my not has to go with one of the quantifiers, and the anyone would be the one it would be. So there does not exist a person that person can fool. So that would have been not, there exists D, right, for that one. So I would have put there exists P, not there exists D, F of PD. So there's a person who can't find anyone they can fool. Okay, we're going to do F now. F says no one can fool everyone. So we know that's a for all. We know that's a not there exists, right? Whoever's doing the fooling is going to be P. Who's being fooled is a D. Right, F of PD. By the way, you don't have to do that. It's just going to be less confusing if you use P as the people doing the fooling and D as the people being fooled. You could write other letters. You could use hearts and teddy bears. But I'd rather if you didn't. If you have time to do art on your test, I need to make a longer test. So, okay. So no one can fool everyone. Same order as the English. The other thing you can do is write the statement for someone can fool everyone and then put a not on it, right? So if the English sentence has a not on it, like at the beginning, you know that the opposite, you know how to write the opposite, which is a positive statement that doesn't have a not, and then just put a not on the front, which is pretty much what this is anyway. Okay, our last one is Andy can fool exactly one person. So we don't have a quantifier for exactly, so we need to do at least one. So we're going to write the predicate calculus for at least one first, and then we're going to fix it to make it exactly one. All right, so Andy's doing the fooling. There's a person he can fool. And since I said there is a person, that's going to be a there exists. So in order for him to do exactly one, there has to be one, right? Now what I like to do is pretend that there's another person that he can fool. And I have to put D doesn't equal F because otherwise, if I make a variable, it could be the same variable that I had to begin with. So I'm going to suppose that person exists. That is different than my first person. Now, does that person exist? No. So I add those two statements together, but I negate the second one because that second person doesn't exist. So the first one does, but the second one doesn't. So if I wanted to do exactly 2, I would do the same thing, right? Except I wouldn't have negated that one. I would have just said there exists D and there exists F and there exists G, but I would have negated the G, right? And I would have D not equal to F, F not equal to G, and D not equal to G also. I have to have all three of those if I do exactly 2. So I'm going to change this for exactly 2 so you guys see how to do it. So you just copy this statement. So I have to verify that the third one isn't the same as the other two. And that third one doesn't exist. The other way you can do it, if your brain works better that way, so this last statement can be rewritten to say that if there's a person that can be fooled by Andy, then they have to be D or F. So these two things, so line 1 and 2 are logically equivalent. So either one of those last statements will work. You may also put your quantifiers at the beginning, so they don't have to be on each row, but that's how I like to do it because it keeps my stuff straight. Any questions? Okay, with the last 6 minutes, we will do a proof problem. Does anybody recognize this problem? You should, because I've done it in class and it's on the NovaNet tutorial, right? We're going to do it by direct proof. So we did it by contradiction before. So there are two things I recommend that you do first. There's two options. One is you look for something that has a B on it, and you figure out how to get rid of the other variables on that line. Or the other option is line 3 sort of looks like what we sometimes get with negation of conclusions. So I might want to actually distribute that knot with De Morgan's and figure out what those pieces are. So you can do either one, I recommend. So try that for a minute, and I'll do a couple of those steps. Okay, so going from lines 4 through 7 should be relatively straightforward for you because we're basically doing the implication rule and then applying De Morgan's and doing simplification. So we can only do simplification with ands, and remember you can't do that simplification with anything if it's part of a line. You can only do simplification if and is the main operator on your line. So if there's a knot on the outside, that is the main operator, and you're not allowed to do anything with the inside until you figure out how to distribute that knot, because knots turn things into lies. So everything on the inside of a not statement is a lie. And implications do that too, right? So if I have an implication, part of it could be a lie because the left side is negated in an implication. So we got to be careful. All right, so we have A and we have not D. And in order to get the B, which I really want, I can use A to get that with line 6. And the rule for that is modus ponens. So we got B, yay. The next thing I want to get is not C. Does anybody see how I could get it? So what lines am I going to use? 2 and 7. And we're going to use modus tollens because that's the one that tells us if we're not getting wet, then it must not have rained. So we have not D. It's going to basically cancel out that one and give us C, not C. So we can now do conjunction to get B and not C. And we're done. We will see you next time for the test.